Hi, I'm Hojun Jang from Seoul National University 3D Vision Lab, and I'll present our work, ReMP, Reusable Motion Prior for Multi-Domain 3D Human Pose Estimation and Motion Inbetweening. I will first introduce our work. We train a reusable motion prior from a large-scale motion dataset. Then, we use the pre-trained motion prior for the motion task. We first estimate the 3D human pose from diverse sensors, including depth point cloud, LiDAR scans, and IMU sensor data. We can also in between the missing frames when the blue keyframes are given. I will now explain the method of our work. We use a two-stage training pipeline. We first train the motion prior, and then we use the pre-trained prior for the motion estimation. For the first motion prior training phase, we use a transformer-based VAE architecture. We combine the SMPL pose parameter and the transition of the root translation to form a motion parameter M, and use as an input and output of the VAE. The posterior distribution is learned from the reconstruction loss, and the prior distribution follows the posterior distribution by using a KAL divergence loss. After fully training the motion prior, we freeze the network parameters and start to train the reusing part. For the reusing phase, we encode the sensor inputs using an input encoder. For the point cloud inputs, such as depth point cloud or LiDAR scans, we use PointNet as an input encoder. And for the IMU sensor data, we use MLP as the input encoder. The transformer encoder then makes the distribution from the encoded input features, and the estimated distribution is encouraged to follow the pre-trained prior distribution. Also, an additional shape estimator is used to make shape parameters from the input features. Shape estimator is trained by minimizing the errors to the ground truth shape parameter. Estimated SMPL parameters are then combined to generate full reconstructed human motion. We use a large-scale motion data of MS to train the motion prior. Then we generate a synthetic dataset of each input modality using the motions of MS to train the reusing part. After training ReMP with synthetically generated data, we evaluate ReMP on real-world datasets. We will show the experimental results as shown in this slide. For the depth point cloud, we tested on our synthetically generated CMU dataset, and also on Berkeley EMET dataset, which is a real-world dataset. Next, for the LiDAR scans, we applied ReMP on real-world Sloper 4D dataset. For the IMU sensors, we tested also on real data included in total capture dataset. Finally, we present results on motion in-betweening task. This is the result of ReMP when the synthetic depth point cloud is an input. We visualize per vertex errors with the colors. This is the result of ReMP with the baselines. ReMP shows the most consistent and accurate motion compared to the baselines. This slide shows the motions play slowly. This is another result on synthetic depth point cloud. The baselines fail to reconstruct accurate motion on extreme movements. This is the result on real depth point cloud dataset. There are no ground truth pose in the dataset, so we only visualize the reconstructed motion without colors. There are more noise in the point cloud so that the performance of the baselines decreases. ReMP shows the most consistent motion among the methods. This is another result from the real depth point cloud. Jang's method also estimates well in this scenario. However, arms in the result of ReMP best matches the input point cloud. This is the result when the real-world LiDAR scans are given. LiDAR scans are much sparser than the depth point cloud, so that the baselines fail to recover accurate motion. Compared to Jang's method, ReMP shows better performance in estimating the position of the hand. This shows the result when the input scans are noisy. ReMP shows the best performance even in noisy input data. This is the last result on LiDAR scan input. Now is the result from the IMU sensor data. We only visualize ground truth mesh without showing the IMU sensor data. ReMP shows the best performance on estimating the root translation. This is another estimation result from the IMU sensor. The vertex errors of the baselines are significantly larger than ReMP. This is the last result of estimating the motion. This slide shows the result of motion in-betweening. Blue frames are the given frames, and we compare the result with spherical linear interpolation method. The feet in the result of SLURP do not alternate correctly. Motion in-betweening in more complex motion is shown in this slide. This is the final slide for the results. To conclude, we propose ReMP, which learns rich temporal correlations of detailed 3D human motion from large-scale dataset. And ReMP maintains robust performance in real sensor noise without further fine-tuning, even if the model is trained only with synthetically generated data. Additionally, the temporal information accurately filled in the missing frames of the motion sequences. We expect ReMP to be adapted in various real-world applications that require fast and accurate 3D human pose estimation under unknown adversaries. Thank you for watching.